Hi, welcome. Thank you for coming. It's such a nice day. Raining, not raining, raining, not raining. Thank you for coming. This is the third in the revamped lecture series, the public lecture series on Wednesday nights at Harvard. And this is kind of an exciting one. Gamma ray bursts are one of my favorite kind of bursts. And they're very, very recently in astronomy, they're very, very interesting. So I'm kind of excited about this talk. I don't know everything. Berger is a professor in the astronomy department, and he's actually the John L. Loeb Associate Professor of Astronomy. He comes from Israel, but went to school at UCLA and won a whole bunch of prizes, like best guy in the astronomy department. You can read here the actual name. For instance, the E. Lee Kinsey Prize for outstanding graduate. And then he went on to Caltech, which is an amazing graduate school in astronomy, where he did his PhD. He did a number of postdoctoral fellowships at really interesting places, and then, of course, came to the most interesting place here at Harvard, where he teaches Astronomy 100, and where he works on looking at gamma ray bursts from many different telescopes, which he'll tell you about all over the world. And apparently he doesn't have to go there, he just phones. He's going to tell us about that. Anyhow, I'm really excited to hear him talk, so let's just go ahead and hear about gamma ray bursts.
Okay, thank you everybody for coming out this evening. So before we start, I have a confession to make. I love gamma ray bursts. Okay, I really do. I find them fascinating for a variety of reasons that I'll tell you about tonight. First and foremost, they push astrophysics to its real limits. So the objects that are involved in producing gamma ray bursts are things like the most massive stars in the universe, colliding neutron stars, the birth of black holes. So this is really the extremes of what we know about in astronomy and physics, and I will tell you about this today, how we reach those conclusions. Gamma ray bursts also push astronomy itself to the limits, observational astronomy. So most astronomical objects that we're used to when we go outside and look at the night sky, maybe not on a night like this, are there night after night, right? We always see the same stars, same Andromeda galaxy, etc. But gamma ray bursts are very different. They last for only a few seconds up to maybe a few hours. And so they push the way we do astronomy into a very different direction. We have to use the biggest telescopes in the world on a very short notice. And I'll tell you today how that works, how we actually capture and study these objects. But I think most of all, I find gamma ray bursts fascinating because they epitomize the idea of scientific serendipity. A discovery that was completely unexpected. Nobody has ever predicted that gamma ray bursts should exist. They were discovered completely by accident. But that discovery really set off a chase that lasted for several decades and is still going on today, involving hundreds of astronomers around the world and almost every single observatory in existence. And so what I want to do today is take you along on this chase that has started about 40 years ago and show you what we've learned over the last few years. Now, if none of that is enough, then here's another motivation to think about gamma ray bursts. So here's an article from Sky and Telescope from a few years ago about gamma rays of doom, why you should worry about merging neutron stars. And here's an artist's conception of what would happen if a gamma ray burst exploded somewhere in the Milky Way galaxy and incinerate the Earth's atmosphere. Okay, so if nothing I said so far caught your attention, this should, right? You should really worry about these things. Okay, so let's set the stage. Before we talk about what gamma ray bursts are, let's talk about what gamma rays are. So gamma rays are a form of light. They're part of the electromagnetic spectrum that we're familiar with radio waves at the longest wavelength end of the spectrum, the visible part of the spectrum that our eyes are sensitive to, and then the ultraviolet, X-ray, and finally gamma rays as the most energetic form of light, with a wavelength that's about the size of an atomic nucleus, okay, and hence the large energy. So this is really the most extreme form of light that we know about, and one of the important aspects of gamma rays that are critical to our story of gamma ray bursts is that they cannot penetrate the Earth's atmosphere. Now that's a good thing, right? Because the atmosphere protects us from the harmful effect of gamma rays. It also means that if we want to detect any source of radiation that produces gamma rays, we have to go above the atmosphere. So our story of gamma ray bursts starts, like any good James Bond movie, starts at the height of the Cold War, the early 1960s. And the US and the Soviet Union were carrying out larger and larger nuclear tests. And eventually they realized that this was not sustainable, and they decided to sign the Limited Nuclear Test Ban Treaty in 1963. And the critical part of the treaty that's important to our story is that it prohibits, prevents, and do not carry out any nuclear weapon tests in the atmosphere beyond its limit, including outer space. Okay? And here's a picture of President Kennedy signing the treaty. Now, there's very little trust between the US and Soviet Union about whether they will keep to that treaty, particularly the aspect about nuclear tests in outer space. And so the Department of Defense started a program called the Vela satellites, shown here. So you can see these are relatively modest-sized satellites that were designed to detect the signature of a nuclear test in space. And that signature is a burst of gamma rays that will occur at the time of the explosion. Now, they launched these satellites in pairs. And the reason was that using a pair of satellites, they could triangulate the direction from which a nuclear test would come and could verify whether the Soviets violated the treaty. So the first of these Vela satellites were launched in 1963, and the program lasted for several years. Now, things got really exciting in 1967. And so one of these pairs of satellites was looking and suddenly saw this large burst of gamma ray radiation that lasted about 8 seconds. Okay, so let me play that again, because this is essentially, will give you kind of an idea. This is a real-time, a gamma ray burst. And so you can see how long they last. So there is just nothing, and then for a few seconds, a large burst of gamma rays, looking very much like the signature of a nuclear explosion. Okay? And so you can imagine that this created a lot of excitement. But then the satellites detected another one, and another one, and another one. And of course, they had the ability to triangulate where these explosions were coming from. And so eventually it was realized that these bursts were not due to nuclear tests. Okay? They did not come from just outside of the Earth's atmosphere or from the moon, which was another possible site for nuclear tests. And so the information was declassified in 1973, and 3 scientists from Los Alamos National Laboratory published a paper in April 1973 on observations of gamma ray bursts of a cosmic origin. And they stated 2 primary facts in particular. One is that the durations of these bursts lasted anywhere from 1/10 of a second, only 1/10 of a second, up to about 30 seconds. So there's a wide range of durations for these bursts. And perhaps the more important fact, the directional information, the ability to triangulate these events, showed that they did not come from our local part of the solar system. They were not coming from outside the Earth or from the sun or from the moon. Okay, so they were either in the outer parts of the solar system or beyond. And this is really the paper. This is a very short paper. It's only 4 or 5 pages that set off this chase to study gamma ray bursts for the subsequent 40 years. So here's a gallery of gamma ray bursts, just to show you what we're talking about. So each one of these diagrams is the number of gamma ray photons detected as a function of time. And you can see that they come in all shapes and forms. Some of them are very smooth. They go up and then just decline smoothly. Some of them are extremely chaotic. Some of them are a couple of spikes. Some of them are many spikes. Some of them last for hundreds of seconds, and some of them are as short as 10 milliseconds. Okay. And so as the saying goes in the gamma ray burst field, if you've seen one gamma ray burst, you've seen one gamma ray burst. Okay? There's just no regularity at all in their properties. Now, gamma ray bursts are extremely rare. We detect about, or we think there are about 3 gamma ray bursts per day in the entire universe. Now, that may sound like a lot. So to give you a scale, supernova explosions, which are also relatively rare events, 1 per century in the Milky Way, occur 1 per second in the universe. Okay, so you can actually count time with supernova. You can do 1 supernova, 2 supernova, 3 supernova instead of Mississippi. right? But just think about those relative scaling, 1 per second versus 3 per day. These are extremely rare events. Okay, so how is it possible that we never knew about gamma ray bursts? Then we launched these very primitive satellites, and the first thing we discover are these gamma ray bursts. The reason is that they're extremely bright. And so to give you kind of a sense of scale of how bright these events are, here's a map of the sky in gamma rays. Okay, so this bright region over here is the Milky Way galaxy that we live in. And then you can see that as you move away from the Milky Way, the sky in gamma rays becomes darker and darker. There are only a few sources. And the reason is that gamma rays are an extremely energetic form of light. It takes very unique types of objects to produce gamma ray radiation. Now let's take a look what happens when one of these gamma ray bursts takes place. So here's the same map, and here's a gamma ray burst. You can see it up here. Boom. Look at this. Okay? For a few seconds, 5 or 10 seconds, it outshines the entire universe in gamma rays. Okay? Think about this for a second. This is a single event that outshines the entire universe for a few seconds. So that's the reason even a primitive satellite, as soon as it was launched, could detect these events. But it also gives us an idea of what kind of events we're dealing with. Now, another interesting fact is that I showed you this little cartoon picture at the beginning of a gamma ray burst incinerating the Earth's atmosphere. That hasn't happened yet, as you probably all know. But gamma ray bursts actually impact the Earth's atmosphere. So here's a plot of the depth of the ionosphere, which is part of the atmosphere. And you can see some day to nighttime variation. And here is a gamma ray burst that occurred. And as you can see, it just pushed the ionosphere down. Okay, so this is an event that occurred somewhere far out in the universe, maybe in the outer parts of the solar system, maybe somewhere else in the Milky Way, maybe at the edge of the universe. But it actually had an impact on the Earth's atmosphere. Okay, so again, that gives you a sense of scale of how energetic these events are. Okay, so the discovery was announced in 1973, and the first 2 decades after that were fantastic. Okay, there was very little information, and so everybody had a theory about what gamma ray bursts are. And this is an actual compilation of all the theories that were proposed to explain gamma ray bursts by the early 1990s. 135 different theories to explain these objects. And at the time, there were less than 100 gamma ray bursts known. So in physics or in astronomy, this is a fantastic time, right? You have more than one theory per event. Theorists had a fantastic time. Now, a lot of these theories had some common themes, and the reason is that the 2 basic facts that were known is that these are events with a very short duration, less than a second up to maybe tens of seconds, and produce extreme energies. They produce gamma rays. And so the question was, what could produce these properties? And people came up with a variety of ideas. For example, maybe it's some new type of exploding star, something different from a supernova. Maybe these are giant flares. We see flares on the sun, which are not as large as these, but maybe these were giant flares on other stars. Perhaps there were the annihilation of matter and antimatter. So one theory was that if there are antimatter comets orbiting other stars in the galaxy, when one of these antimatter comets collided into a star made of matter, it could produce a gamma ray burst. Or maybe something to do with black holes. Black holes are very exotic events. Maybe they can produce gamma ray bursts. And there was even a suggestion of interstellar warfare. After all, these satellites were designed to detect nuclear explosions. So maybe these were really large nuclear explosions. Maybe other civilizations just blowing up whole planets. Okay. So there was quite a lot of interest in this and quite a lot of ideas. Now, the reason there were so many theories floating around is that there was one basic problem, which is that there was an uncertainty in the distance to the gamma ray burst that was about the size of the entire universe. Okay? And that means that the energy scale was also not known. So it was just, the only thing we knew was that they were coming from outside of the local part of the solar system. And of course, if these events were in the outer parts of the solar system versus the edge of the universe, they would require a very different energy scale, and therefore a very different mechanism. Now, why did we have this problem? The reason is that these satellites were extremely efficient at detecting these very bright bursts of gamma rays, but they were not efficient at localizing them in a precise way. And so when a gamma ray burst would occur, the satellites would detect it, and they could say, well, it came roughly from that area on the sky. Okay, so then you go and you take a picture of that area on the sky, and what you see is something like this, right? There are a lot of different sources. So maybe the gamma ray burst was associated with that star or that galaxy or maybe that galaxy or this collection of stars. It is really unclear. And of course, some of these stars are close to us and some of them are really far away. Some of these galaxies are extremely distant. And so without actually being able to associate the burst with a specific object, there was no way of understanding how much energy these objects produce. Okay, so that was really the main challenge. Now to scale, just to give you an idea, this is the side of the moon on the sky. So these regions on the sky were just very large. Now there was one test that was clear. And the question was whether gamma ray bursts came from the Milky Way galaxy. If we could at least say whether they came from the Milky Way or outside of the Milky Way, that would already give us some indication of what was happening. So here's our Milky Way galaxy. We are part of the disk of the Milky Way. So most of the stars and the objects in the galaxy are located along this thin slice of the sky, following the plane of the Milky Way galaxy. So if gamma ray bursts came from the Milky Way galaxy as opposed to outside the Milky Way galaxy, we would expect that they would line up with the disk of the Milky Way galaxy, right? If we made a map of the locations of gamma ray bursts, it would look something like this. Most of them would be concentrated along the plane of the Milky Way galaxy, and there would be very few of them away from the galaxy. Okay? So here is a very clear test. Even though we can't localize these bursts individually to a precise position, we can at the very least see if they line up with the disk of the Milky Way galaxy. And so in 1991, NASA launched the second of its great observatories, the Compton Gamma Ray Observatory. The first one, of course, was the Hubble Space Telescope. And one of the main objectives of the Compton Gamma Ray Observatory was to discover a large number of gamma ray bursts of order 1,000 or several thousand, and localize them well enough that we could see whether they come from the Milky Way galaxy or not. And the instruments that were designed to detect these bursts are seen here on the corners. And so they were pointed in all parts of the sky to find these gamma ray bursts. And here's what they found after several years of observations, collecting one gamma ray burst after another, and eventually they released a map of the location of gamma ray bursts after they had about 2,700 of them. All right. So how many people think that gamma ray bursts come from the Milky Way? Nobody. How many people think gamma ray bursts come from outside of the Milky Way? Everybody. Okay. Good. So it turns out you're smarter than most astronomers, because when this map was released, NASA decided to, the American Astronomical Society decided to have a great debate to actually finally answer the question of where did gamma ray bursts come from. And I will show you in a second what the answer was. But the occasion in 1995 was the 75th anniversary of the great debate on the scale of the universe that took place in 1920 between Shapley and Curtis. And back then, the argument was whether the nebulae that were discovered by Hubble were part of the Milky Way galaxy, and essentially that the Milky Way galaxy was the entire universe. That was the view taken by Shapley. Or whether these were island universes, their own galaxies outside of the Milky Way, meaning that the universe was actually much bigger than was thought of at the time. That was the view taken by Curtis. Now, Curtis was correct. These island universes really were independent galaxies, and Shapley was wrong. And so Curtis won the debate in 1920, and Shapley, a year later, became the director of the Harvard College Observatory. That was his consolation prize. Okay, so in 1995, the debate was on this distance scale to gamma ray bursts, okay, echoing the question in 1920. And the argument was whether they were galactic or extragalactic in origin, cosmological. So Don Lamb of University of Chicago argued that they were galactic, and Bohdan Paczynski for Princeton University argued that they were cosmological. Now, you just looked at that same map, and none of you thought they were galactic. So what was the crux of the argument for a galactic origin? Well, around the same time, people discovered neutron stars, pulsars, that were traveling out of the Milky Way galaxy at speeds of hundreds of kilometers per second. Okay, so these were neutron stars that were born in supernova explosions, And during this explosion of the star, they somehow received a very large kick that ejected them outside of the Milky Way at these very large speeds, creating this sort of uniform distribution of neutron stars in the halo of the Milky Way galaxy. And so the argument was that if gamma ray bursts had something to do with those neutron stars, then even though they were all related to the Milky Way galaxy, they might actually give a distribution of the sky that looked very much uniform. Okay? So that was the argument. And here's a picture at the end of the debate. Here's Paczynski and Lamb, and this is Sir Martin Rees, who's the Astronomer Royal of England. He's supposed to advise the Queen on comets and things like that might pretend disaster. But you can see that they're all in a good mood. And the reason they're in a good mood is because there was a vote at the end of the debate and it came down 50-50. Okay, so people really could not decide, even after having that information, whether gamma ray bursts were galactic or extragalactic. Now, the reason people were hesitating is because if gamma ray bursts were cosmological in origin, if they came from the far reaches of the universe, that indicated such large energies that most people were not comfortable with that idea, that there are mechanisms in the universe that can produce these kind of energies. So people were much more comfortable with the idea that they were galactic, and yet some of the evidence was pointing in the other way. So this was not enough to solve the mystery. Now, one thing was recognized by a lot of theoretical astronomers was that just like when you light a fire and initially you have these large flames, they're very bright, it's easy to see them from far away, eventually the flames die away and you're left with this glowing embers that last much longer. They're fainter, they're harder to see, but they last for a lot longer. So there was an analogy that was made that if the gamma ray burst could be like that initial fire, a lot of energy getting released in a very short period of time, a second, 10 seconds, 100 seconds. But maybe there was a hope that this would be followed up by these glowing embers, by an afterglow that would last for maybe a few hours or a few days. And if we could capture this afterglow, we have longer time to actually go and find it. And because it produced most of its radiation at energies that we know how to work with, not gamma rays, but ultraviolet and visible light and radio waves, we might be able to pinpoint the positions of the gamma ray bursts much more accurately than from the gamma rays alone. And so we can use the afterglow to tell us where the gamma ray burst came from, and therefore decipher the origin of these bursts. Now, this requires a very different approach. So this is actually the approach that we take and have been taking for several years now to study gamma ray bursts. So let me just show you what we do when one of these things occurs. So we have satellites in space that are gamma ray satellites designed to find these gamma ray bursts. And these modern satellites are fantastic. As soon as a gamma ray burst happens, I get an alert on my cell phone within about 30 seconds of when the burst occurred. I get an alert on my iPhone that tells me where on the sky it is. And then my research group, calls up all of these observatories around the world, and we tell them, please stop what you're doing and repoint a telescope to that position where the gamma ray burst just occurred. Okay, and we have to do it within minutes, otherwise this afterglow will fade away and disappear. So these are not just nice gratuitous pictures of telescopes around the world. These are really the facilities that we use, or at least some of them. The Magellan telescopes in Chile, the MMT telescope in Arizona, the Gemini telescopes, which are located in Hawaii, the Very Large Array in New Mexico, and then some telescopes in space. Of course, we don't get to go to those. But we really just phone up the observatories, and whoever is using the telescope, we ask them to stop what they're doing and look at the gamma ray burst. And as you can imagine, as a result of that, we have a lot of friends. But you know, people like being part of this endeavor. At least that's what I tell myself. So here's kind of a little movie that shows how the sequence of events occurs. So somewhere in the universe, the gamma ray burst occurs, and it's detected by a satellite, and the information is sent down to the ground, and you can see the telescope is already moving. They responded very quickly. And then we take images of the sky, and we look for an object that fades away. That will be the afterglow. Now, of course, in real life, it doesn't come with a circle around it. Right? So we have to actually do a lot of hard work to find what this afterglow is and where it is. But this is, in a nutshell, what we do to capture these gamma ray bursts. And again, we have to do this in minutes or hours. Otherwise, we lose that burst, and we have to wait for the next one. Now, with the current satellites, we find about 2 gamma ray bursts per week. Okay, so we run around twice a week to do this, and we've been doing this for several years. And for some reason, it always seems like they happen on the weekend, those 2 per week. But still, it's a lot of fun. Okay, so this idea of capturing the afterglow came to fruition in 1996 when the Dutch and Italians decided to launch a satellite that could provide positions for the gamma ray bursts that were 100 times more accurate than the Compton Gamma Ray Observatory. Okay? The realization was it's not enough to just tell whether they come from the Milky Way or not. That wasn't a good enough test. We need 100 times more accurate positions. And more importantly, those positions have to be sent to the ground within a few hours. Otherwise, the afterglow will fade away. Now, these days, it takes 30 seconds. With this first satellite, it was about 8 to 10 hours. Okay? So the satellite was launched in 1996. And they had their first success in February, March 1997. They discovered a gamma ray burst on the satellite. And then the satellite had an X-ray telescope to look for the afterglow. And here's an image from the X-ray camera taken on February 28th. And here's an image of the same part of the sky 3 days later. And you can see a bright source in X-rays over here that faded away. So this was the first afterglow ever seen from a gamma ray burst. And it really vindicated this whole idea that by studying the afterglows, we can determine the origin of gamma ray bursts. Now, we are interested in particular in afterglows in visible light, not X-rays. And the reason is twofold. We can pinpoint sources in visible light much more accurately than in X-rays. And the other reason is we can use the visible light to actually allow us to measure the distance to the gamma ray burst. So here's what afterglows look like in visible light. So here is, again, an image taken a few hours after a gamma ray burst explosion, and an image of the same part of the sky taken a few hours later. And here, again, shown by an arrow, is an object that was bright over here and faded away over here. This is the afterglow. Here's a nice little movie showing another afterglow. This one, you can see occurred over here and then just dims away over the course of several days. Now, what's fascinating about this little movie is you can see these objects over here, this one, this one, this one. Those are galaxies. Those are galaxies like the Milky Way, okay? Hundreds of billions of stars. And here is the visible light from this afterglow, and it is about 1 million times brighter than an entire galaxy. Okay? So even though the afterglow is fainter than the gamma ray burst itself, it's still amazingly bright. Okay? And that allows us to actually capture these afterglows and study them in great detail. Now, why do we care about the visible light in particular? Well, the reason is that we can use the visible light to measure a redshift. Okay? So the concept of a redshift is relatively straightforward. We're all used to this from sound. If a train approaches us or moves away from us, we hear a different pitch. The same thing happens with light. If a source moves away from us, the light is red-shifted. If a source is approaching us, the light is blue-shifted. And since the universe is expanding, there is a direct relation between the amount of redshift and the distance. Sources that are further away from us are moving away from us at a larger velocity, a larger speed, than sources that are nearby. So by measuring the redshift to an object, we can directly relate that to the distance of the object. So if a gamma ray burst is inside the Milky Way galaxy, of course the Milky Way galaxy is not expanding, it stays the same size, so there will be no redshift. If gamma ray bursts are in the relatively nearby part of the universe, they will have a very small redshift and a small distance. And if they're very far away, they will have an enormous redshift and a very large distance. Okay, so we can measure this from the visible light in a direct way. So here's an example of how we do this. What we do is we find the afterglow in visible light, and then we take a spectrum of the afterglow. We pass that light through a prism, we break the light up into its components, and we look for the redshift. And the way we do it is by identifying these lines that are due to various types of elements. So all these lines that you see here are due to elements like carbon and silicon and magnesium and iron and aluminum. And we know the lines, we know what the rest wavelength of the lines is, and therefore we can measure by how much they are redshifted. If the redshift is 0, then gamma ray bursts are in the Milky Way. If the redshift is very large, they're in the far reaches of the universe. And so from this spectrum, for example, of a gamma ray burst, by identifying all of these lines, we can measure the redshift, we can measure the distance, and here is what it is. 12.1 billion light years. Okay? So that means that the light from this burst has been traveling to us for 12.1 billion years. That's over 90% of the history of the universe. Okay? That means that this burst, this gamma ray burst, occurred when the universe was only 10% of its current age. It is extremely distant. Not only is it not in the Milky Way, it's nowhere in our vicinity. Okay? This is an ancient object. And so that means that with these kind of enormous distances, gamma ray bursts really are so energetic that they are the biggest explosions since the Big Bang. In fact, to give you a sense of scale of how much energy is required to produce a gamma ray burst, everybody knows Einstein's famous equation, E equals mc squared, right? Okay, so if we take the sun and convert all of that mass to energy, pure energy, using E equals mc squared, that's how much energy a gamma ray burst produces. Okay? So think about that for a second. You take an entire star and convert it completely into energy, and that's the scale that we're talking about. Okay, so these are really enormous explosions. And really the only way we know in nature to do this is through the formation of a black hole. Okay, so by forming a black hole and then accreting the material into the black hole, we can release these kind of energies. And so from 135 theories that were proposed in the early 1990s, by measuring the distances to gamma ray bursts, we've essentially narrowed things down to one theory, which is that gamma ray bursts essentially mark the birth of a black hole. That's what they are in their simplest form. Now there's a little bit more to the story. So far I've told you that there are gamma ray bursts, and I've pretended as if they're all one group of objects. It turns out that there are actually two different categories of gamma ray bursts. So if we look at the duration, the distribution of duration of gamma ray bursts, all the way from 10 milliseconds down here to about 1,000 seconds here, you can see that there are actually two groupings of gamma ray bursts. There are ones that are about shorter than a second, and another large group that are longer than about a second. Okay, so astronomers are very inventive with names, so we call these the short ones, and we call these the long ones. And you can see two examples over here. They essentially look the same, just some of them are shorter and some of them are longer. Now, the fact that there are two groups, two types of gamma ray bursts, suggests that maybe there are actually two ways of producing gamma ray bursts. We know that we need to do it through the birth of a black hole. You know, maybe nature has found a way of doing this in two different ways, which would be quite astounding, that we can form black holes in two completely different ways. So let's think about this. So one way of forming a black hole is to take an extremely massive star, something like 100 times the mass of the sun. These massive stars have a very different life from the sun. The sun will live happily for about 10 billion years. These very massive stars, they're born and they die within about 10 million years. Okay, so they're kind of like the rock stars of the universe. They kind of live fast and then they flame out and explode. So if we take one of these very massive stars, at the end of its life, it collapses under its own weight and it can produce a black hole. And then that can give rise to the burst of gamma rays. So here is a little simulation showing the process. You can see the star collapsing down to feed a black hole, and then the gamma rays emerging out. And here's an actual computer simulation that shows how this process occurs. Here's the black hole in the center. Here is the jets of radiation emerging out. And you can see that they burrow their way out of the star. And once they get out of the star, they will produce a gamma ray burst. And you can see a little clock running up here. So this is 5 seconds, 6 seconds. It takes about 10 seconds for this to blow out of the star. So maybe these that take about 10 seconds to occur are these long gamma ray bursts. Okay, so that's one way. There's another way to make black holes, which is through the merger or the collision of two neutron stars. Now, neutron stars are fascinating objects in their own right. Neutron stars weigh about 1.5 times the mass of the sun, but they're about the size of the city of Boston. Okay, so these are extremely dense objects. Still not as dense as a black hole, which is, of course, infinitely dense. But that's not too bad, right? I mean, 1.5 times the mass of the sun packed into a few kilometers in size. Now, sometimes these neutron stars are born in a binary system. There are two of them. And as they merge, as they come closer to each other, they can eventually collide and merge to form a black hole. And that can, again, lead to the formation of a gamma ray burst. Okay, so this is a very different mechanism. Now you can see, again, a little movie over here that shows you how these two neutron stars approach each other in their orbit and eventually merge, collide, and annihilate to form a black hole. And that gives rise to a jet of gamma rays. And here's, again, a computer simulation showing that, at least on a computer, this works. Okay, so here are the two neutron stars. They come into contact. They form a black hole in the center here. For some reason here, the black hole is blue. But we can use our imagination. And then there's a disk of material that will drain into the black hole and will power the gamma ray burst. Okay, so those are two very different ways of producing a gamma ray burst from very different types of objects. Here you can see another counter. It shows 1 milliseconds, 2 milliseconds, 3 milliseconds, 5 milliseconds. So this is a very short time scale compared to the other types. So maybe these are the objects that produce the short gamma ray bursts. So we can test this, and this is something we've been doing for the past several years. We can ask the question, if gamma ray bursts are produced by the most massive stars in the universe, where would we expect to find them? Well, remember, I told you that these very massive stars have a very short lifetime. Okay? They die within a few million years of when they were born. That means that we're going to find those gamma ray bursts, if these are the objects that produce them, at the same place where stars are born. Right? They're born and they die so quickly that they're still in the same environment. That means that we're going to find them in stellar nurseries, in environments like these where young, massive stars are born. That's also where they die. Now, where do these star nurseries occur? So here is a view of the Whirlpool galaxy. This is what the Milky Way would look like if we could look at it from the top. And you can see these spiral arms are dotted with these very bright regions. And these are regions where star formation occurs. So in these spiral galaxies, most of the stars are born along the arms, whereas most of the old stars are here in the center. So if gamma ray bursts came from these very massive stars, we'd expect to find them along the spiral arms of the galaxies in which they occur. And here is a nice example. Here is a galaxy that produced a gamma ray burst and then was imaged with a Hubble Space Telescope. And so you can see the center of the galaxy over here, and you can see the spiral arms over here. And this is the location of the gamma ray burst, right along one of these spiral arms, exactly where we expect to find these very massive stars. But there's another place where a lot of young massive stars are born. That other location is when two galaxies merge together. And so here is actually a beautiful example, the antennae galaxies. These are two galaxies that came in together and are in the process of merging into a single galaxy. Now, if we zoom in on this region over here with the Hubble Space Telescope, you see all of these blue knots of very bright objects. These are all environments where young stars are formed due to the collision of these two galaxies. So once again, if gamma ray bursts come from these very massive stars, we would expect to find them in galaxies that are in the process of merging. And again, here are Hubble Space Telescope observations of galaxies that produce gamma ray bursts. And you can see this galaxy is in the process of merging together, two galaxies that are coming together. It almost looks like these antennae galaxies. Here's another example of several galaxies in the process of merging, and the gamma ray burst occurred over here. So it looks like the long duration gamma ray bursts are really occurring in the same environment where we expect to find the most massive stars in the universe. So that gives us a very nice clue that this is really what produces these long duration gamma ray bursts. Now, what about these mergers of neutron stars? Well, that's a very different story. So in order for the neutron stars to merge, they need to start from a large separation and slowly spiral in until they come into contact. And that usually takes billions of years. Not 10 million years, but billions of years. So that means that by the time those systems come together to merge, all the other stars, the massive stars in the galaxy, have all died away. Right? They've been long gone, and the only stars that are left behind are old stars, like our sun. So we would expect to find these systems in these elliptical galaxies, these dead elliptical galaxies that are no longer forming any young stars. They look very boring, right? They don't look as pretty as the spiral galaxies. But that's where these short, or these gamma ray bursts that come from mergers of neutron stars would occur. So if we go and we take images of the galaxies that produce short gamma ray bursts, here's what we find. These boring, round looking things, elliptical galaxies. And so here, again, we have direct evidence that the short duration gamma ray bursts are occurring exactly in the environments where we expect to find only these old systems, these merging neutron stars. And so it turns out that from these kind of lines of evidence, and there are other ones, that long duration gamma ray bursts really come from these extremely massive stars, whereas the short duration gamma ray bursts are produced by the collisions of two neutron stars. And it's amazing that nature found two very different channels to produce objects that look almost identical in every respect except for their duration. Okay, so this is kind of where we stand now. And of course, there are a lot of details that we try to understand, but we've gone a long way from not even knowing whether these objects were coming from the outer parts of the solar system to the far reaches of the universe. We've actually learned an enormous amount. And you can say, okay, that's all great, but what have gamma ray bursts done for me recently? So let me tell you a little bit about where we're going next with gamma ray bursts. So one of the big questions in cosmology and in the formation of the universe is, when did the first stars and galaxies in the universe actually form? Okay, so we know that there was the cosmic microwave background that was formed about 300,000 years after the Big Bang. And we know the universe around us today all the way back to about 1 billion years after the Big Bang. We know that there are a lot of stars and galaxies, and we have some basic ideas on how they form and grow over time. But this period of time between 300,000 years after the Big Bang to about 1 billion years after the Big Bang, that's quite a big chunk, is currently called the Dark Ages. We know that the first stars and galaxies must have formed sometime during that period, but we don't know when and we don't know how. And those are two very big questions in cosmology. Now, we can simulate all of this on a computer. Okay, so we can take a model universe on a computer and we can run it forward in time from the Big Bang, and we can watch how galaxies form. But maybe that's right, and maybe it's not. Without direct evidence, we really don't know. Right? We don't want to just rely on a computer program to tell us how the universe formed. So what does this have to do with gamma ray bursts? Well, as I hopefully convinced you, gamma ray bursts are extremely bright. Right? They outshine entire galaxies by a factor of 1 million. In gamma rays, they're brighter than the entire universe for a few seconds. So that means that if gamma ray bursts occurred in this early phase of the universe, in particular, if some of the first massive stars in the universe exploded as gamma ray bursts, we could actually see them more easily than we could see entire galaxies. So what would be great is if we could find a gamma ray burst over here, and with our telescope, of course, measure the redshift and get a view of what the universe looked like as this light traverses all the way from the first 100 million years to us. We can look at how the composition of the universe changes over time. We can learn an enormous amount about when the first stars and galaxies occurred, using these beacons of light that only shine for a few hours. Now, until about 2 or 3 years ago, the most distant gamma ray burst that we knew about occurred about 1 billion years after the Big Bang. So right on the edge of the Dark Ages, okay? Which is great, but of course we already know quite a lot about the universe at that time. So one of the goals of my research when I came here to Harvard was to actually find gamma ray bursts in the Dark Ages, actually penetrate this veil and see if we can study the early parts of the universe. And the first part of that was to actually go and find gamma ray bursts in the Dark Ages of the universe. So we've set out to do that, and we've actually succeeded. So here I'm showing you images of 2 gamma ray bursts. One occurred only 630 million years after the Big Bang. The other one only 525 million years after the Big Bang. Okay, so this is a time when the universe was about 4% of its current age. So we're really looking at kind of baby pictures of the universe. And you can see these images of the gamma ray burst, and then it disappears. And the reason it disappears in these images, and it's visible here, is that the redshift is so large that, in fact, we don't see any visible light from these bursts. All the light has been shifted into the infrared part of the spectrum because the redshift is so large. And that's how we measure the distances. And in fact, about 6 months ago, we found another one that's about 700 million years after the Big Bang. And so now we have at least 3 of these gamma ray bursts sitting right smack in the middle of the Dark Ages. Okay? So we've achieved our first goal, which is to demonstrate that gamma ray bursts actually exist in the Dark Ages, and that we can actually find them with existing telescopes. Now, the great thing is we can find them, but these telescopes are not big enough to actually do what we really want to do, which is dissect the light from these gamma ray bursts, take a spectrum, and actually use that to measure the chemical composition of the universe at this very early stages. Now, we expect this chemical composition to be very different from what it is in the universe today, because there were so few generations of stars at that point that they have not fully enriched the universe to the level that we see today. In order to do that, unfortunately, our existing telescopes are probably not going to be large enough. They're large enough to capture the light, but not to dissect it. And so to do that, we really need to go to the next stage. So luckily, that next stage will happen in the next 7 to 8 years. So this is really the future. That's the last thing I want to tell you about. So this is the giant Magellan telescope. This is a computer rendition of what it will look like when it's completed sometime around 2018 to 2020. Each one of these mirrors, it's composed of 7 mirrors. Each one of these mirrors is about 26 feet across. Okay, so this whole thing across is about 25 meters or so. And just to set the scale, here's what the biggest telescopes in the world look like today. And this is what this telescope will look like. Okay? Now, of course, the larger the telescope is, the more collecting area it has, the more light it can gather, and therefore it can see fainter and fainter objects, allowing us to actually dissect the light from these gamma ray bursts in the dark ages. Now, this is an international project. It has actually started. Construction of this facility has started. It will be built in Chile. Chile has now become the premier site for large telescopes. And so work on this is ongoing. And the great thing that I'm excited about is that Harvard is part of this project. And so we will get to use this telescope to study the first stars in the universe. Now, just to show you that this is really happening, here is the first of these 7 mirrors. Okay, so this is at the University of Arizona Mirror Lab, where they produce and manufacture these mirrors. This mirror has now been polished. It took about 4 years from the point of melting the glass to finishing the mirror and polishing it. But these are regular-sized human beings, okay, for scale. So you kind of get a sense of how enormous just one of these mirrors is, and perhaps try to fathom what 7 of these will look like pointed up at the sky. So this is the next stage, and this is, I think, what will really allow us to move away from just trying to understand what gamma ray bursts are to actually using them as probes of the infant universe to get a basic understanding of when did the first stars and galaxies form. Okay, so I want to end here. I hope you enjoyed this 40-year journey from discovery to our first initial understanding of what gamma ray bursts are, and you got a sense of where we stand today. It was a completely accidental discovery. I still find that fascinating, that nobody has ever predicted that these objects would occur, and now we use them to study the early universe. But this is really the next step, finding gamma ray bursts in the first few 100 million years after the Big Bang. So thank you.
Wow, that was an amazing talk.
Thank you.
Yeah. I actually didn't know any of that. I have some questions though, but you can have other people ask questions. Can I start, or does someone else want to start with a question? Go ahead. So those 2 jets coming out of the black hole formation, why does it look like that? Why 2 jets rather than?
Yeah, so the idea is that as this, in both types of systems, so we have a massive star that's rotating rapidly and then collapses, there's a preferred axis, the angular momentum axis, where the material collapses into a disk, and then this axis remains evacuated, and the jet can emerge from that direction.
Is there evidence for that?
Yes, so there's actual observational evidence. We see the signature of this jet in our visible light observations of the afterglow. And in fact, we can actually measure the opening angle of the jet. And so what we found from observations of tens of gamma ray bursts now is that these jets are anywhere from down to 1 or 2 degrees up to maybe 10 or 20 degrees. So some of them are extremely narrow.
Yeah. So I have one more question. You think there are 2 sources. How do you know there's not 3? Because your data at the beginning didn't look like just 2 different things.
That's right. I think that's a very good question. And people have been arguing for a while about whether these 2 groups, somewhere around where they're merged, there's a 3rd group of objects. For now, I think we can explain everything we see with just 2 types of objects that produce gamma ray bursts. as we collect more and more of these gamma ray bursts, we are finding 2 of them every week, there might emerge more evidence for a third population. But right now, we're kind of satisfied with 2.
So there's no new physics.
Well, I think the physics of how to actually form the black hole and how the black hole produces the jet at this point is completely black magic. So when I tell you that a gamma ray burst forms a black hole and then the black hole extracts energy and produces a jet, that's all great, but there's currently no theory that explains how that happens from basic physics principles.
Okay, do you want to come to the microphone to ask a question? Thanks.
So are gamma ray bursts a good source to test gravitational wave? And secondly, is a so-called X-ray universe part of the afterglow of gamma ray bursts?
Okay, those are 2 very good questions. So the first question was whether gamma ray bursts produce gravitational waves. And the answer is yes. In particular, the gamma ray bursts that are formed by the merger of 2 neutron stars. Those neutron stars are 2 very heavy masses orbiting each other and producing an enormous amount of gravitational waves. In fact, the Advanced LIGO Observatory, which is being built now and designed to detect gravitational waves, will primarily see those objects, those neutron stars merging into each other. And so in fact, our hope is that once that observatory gets going, we will see the gravitational wave signal right before the 2 objects merge, and that will be followed up by a gamma ray burst. So that will be our most direct test that these neutron star binaries actually make gravitational waves. Now your other question was whether the X-ray was part of the afterglow. Yes, the X-rays, there's some X-ray emission that comes as part of the gamma ray burst itself. It's very weak. But then the afterglow itself produces additional X-ray radiation.
So that's valid in the general relativity. Virtually no challenge.
From the gravitational waves. Yes, I think that will be a fantastic validation of general relativity. Yes.
Please come to the microphone.
So in the formation of galaxies, there are the idea of massive black holes at the center. Is there any relationship of these gamma ray bursts to the massive black hole formation? Especially in the early dark age.
Yes, that's a very good question. And so the question is whether this very supermassive black holes that are sitting in the centers of galaxies are responsible or related to gamma ray bursts in any way. And the answer is they're not related to the gamma ray bursts that I've shown you, because when we can pinpoint their location, we don't see them coming from the centers of galaxies. We always see them coming from the outside or where the stars are forming, not from the center. There are events called tidal disruption events. So once in a while, in the centers of these galaxies where the massive black hole is sitting, a star can stray very close to the black hole and actually get destroyed by the black hole. Now this is very similar to what is happening here. If you destroy the star near the black hole and then all the material drains into the black hole, you can produce something that looks like a gamma ray burst. And in fact, we saw this for the first time about 2 years ago. There was an event that was discovered by one of these gamma ray satellites that looked initially very much like a regular gamma ray burst, but then ended up lasting for a whole week, which gamma ray bursts never do. They only last for a few seconds. And that event came from the center of its galaxy, where we know that there is a supermassive black hole. And we think it was caused by this process, by a star that just unfortunately strayed too close to the black hole and got destroyed.
So you don't think that there would be gamma rays that could form?
So the actual formation of supermassive black holes is not fully understood, but it's not clear that it will necessarily produce gamma rays, and it probably takes a much larger period of time to produce one of these large black holes. So it will not produce something that only lasts for a few seconds.
Yeah, can you come to the microphone?
So will you be able to measure the amount of primordial lithium to a better precision and answer the lithium problem?
That is a very good question. I think that it's unlikely, because I think that most of that is arising much earlier before we think that any star is actually formed. So that has to do more with nucleosynthesis that happened during the Big Bang itself, in the first few minutes after the Big Bang. And nobody right now thinks that stars can form that early. Our current understanding is that stars form a few 100 million years after the Big Bang. So it's not obvious that gamma ray bursts will contribute specifically to that question. What they will allow us to see, for example, is how how oxygen increased in abundance as the universe became older, how carbon and silicon and the other elements that are important for life, for example, grew in abundance.
So you talk about seeing how in the past, how everything was, how the elements are coming to be. Is it possible to see further beyond where we are right now at the age of the universe? Because obviously we're kind of in a certain spot. Can we look into the future and see where we're going with these elements as far as gamma ray bursts? Have we ever seen something, ahead of where we are specifically in the Milky Way and where the universe is going?
So as we look further and further in the universe, we're essentially looking back in time, right? Because we're relying on light, and light has a finite speed. So as the light travels to us, it takes a certain amount of time. So when we see these gamma ray bursts, we essentially get a view of the universe in the past. There's really no way to turn that around and say, let's try to see what it will look like in the future. So we can get a glimpse of what the universe looks like today by looking just around us in the local vicinity of the Milky Way galaxy. Or we can look at these very distant objects which give us a view of the past history of the universe. But if we have enough information, we can potentially predict what we expect the universe to look like in the future.
Any high school students have questions? Then we'll have an adult.
Two basic points from what you said. So you showed us these very focused beams from both of the ways of forming gamma ray bursts. But so when we observe gamma ray bursts, is it because the beam has swept across the Earth, or are we just seeing some other aspect? And two, the ones that you found that are in the dark ages, presumably they're formed from the young stars, not from the neutron stars. But you didn't mention that.
Yes, so those are, again, two very good questions. So because the beams are so narrow, we will only see a gamma ray burst if the beam is pointed at us, right? Because the beam doesn't move. So it's not like a pulsar where the beam rotates around and we see it once in a while. So that means that if the beams are very narrow, then for every gamma ray burst that we see, there are about 100 that we will never see because those beams were pointed somewhere else. Okay, so in fact, we now know that there are about 100 times more gamma ray bursts than the ones we actually observe due to this effect. Now, as to the other question, yes, the gamma ray bursts that we see in the dark ages are of the long duration variety that we think are due to the very massive stars with very short lifetimes. We don't really expect to see at this early stages of the universe already mergers of neutron stars. Although that's our theoretical thinking right now. The universe might surprise us, and it might show us that perhaps some of these merge more rapidly than we thought was possible. And if we see the short duration gamma ray bursts at these very large distances, there will be an indication that some of these neutron stars are already born and they smash into each other within the first few 100 million years after the Big Bang. But right now, they're all of the long duration variety.
So that was wonderful. Let's thank the speaker again. And